Imagine a world where every physical object, from the stars in the sky to the neurons firing in your brain, is not made of atoms, but of equations. This is the core of the mathematical universe hypothesis, a radical proposition suggesting that math isn't just a tool we use to describe reality, it is reality itself. If we strip away the subjective experience of color, sound, and touch, we are left with a fundamental structural core that is entirely numerical. To understand this, we must look at the unreasonable effectiveness of mathematics. Throughout history, physicists have observed that the universe follows complex mathematical patterns with eerie precision. From the Fibonacci sequences found in flower petals to the orbital mechanics of distant galaxies, nature seems to be speaking the language of geometry. The hypothesis posits that if the universe is indeed a mathematical structure, it explains why it behaves so predictably under the laws of physics. However, this leads us to the concept of the multiverse of structures. If reality is mathematical, then every consistent set of equations must exist somewhere. This isn't just about alternate versions of our timeline. It suggests that there are infinite universes governed by entirely different mathematical constants, where the laws of gravity, electromagnetism, and logic operate in ways our human brains cannot even begin to visualize or comprehend. Critics often argue that math is merely a human invention, a linguistic framework we crafted to organize our observations of the world. But if math were purely a human construct, why would it work so perfectly for phenomena we haven't discovered yet? The idea that we discover mathematical truths rather than invent them suggests that math exists independently of consciousness, acting as the invisible scaffolding upon which our entire reality is hung. As we venture deeper into quantum mechanics, the line between physical and abstract becomes increasingly blurred. Particles exhibit behaviors that seem more like wave functions than solid matter. In this sense, a subatomic particle is essentially a vector in a Hilbert space, an abstract mathematical object. When we peel back the layers of the onion of reality, we don't find a hard center. We find information, logic, and pure symbolic representation. This perspective challenges our traditional understanding of causality and time. If reality is a static mathematical structure, time might just be a dimension we are traversing rather than an unfolding sequence of events. In a mathematical universe, the past, present, and future exist simultaneously as coordinates in a vast, multidimensional grid. We are simply observers navigating a frozen, four-dimensional landscape of logic. The implications for artificial intelligence are equally profound. If our consciousness is the result of complex computation, then we are essentially biological algorithms running on hardware made of atoms. If an AI achieves a level of complexity identical to the human brain, the mathematical hypothesis argues that it wouldn't just be a simulation of consciousness, it would be a genuine, conscious mathematical entity, indistinguishable from the mind of a human. Ultimately, we are left with a humbling conclusion. We are small, sentient sparks looking out at a vast, logical architecture. Whether we are a biological anomaly or a necessary expression of the universe's own internal math, our quest to understand these laws is perhaps the most significant function of reality itself. By decoding the universe, we are effectively the universe learning to read its own source code, one equation at a time.